Here is one last slightly different example of area between curves. Suppose we are asked to find the triangle with between the vertices -1, 2, 1, 4, and 2, -4. If we graph this, we will see what? We have to go as far as up and down, -4. It's a little bit more up and down than left and right. Something like -1, 2, and 1, 4, 1, 1, 2, 3, 4, -1, 2, 1, 4, and the point 2, -4, 1, 2, 3, 4, 2, -4. And hopefully this is very clearly not a right triangle. I wanted this very much to not be a right triangle. So it's not a matter of using the distance formula to find two sides and use 1/2 base times height. That doesn't cut it. What we need to do is find all the equations of the various lines. From, let's see, from 1, 4 to 2, -4, we go over 1 and down 4, so that has a slope of -8. And I love to use this formula. I love to say y minus 4 is -8, x minus 1. Slope of -8 through that particular point. There you go. Y is -8x plus 8 plus 4 plus 12. And that is that curve. And over here we have what? We have a slope of over 2 up 2, that's a slope of 1. And so y, let's use the 1, 4 again. Y minus 4 is 1, x minus 1, so y is x minus 1 plus 4 is plus 3. Oh, we can even see the y-intercept of 3. Yay! So that's those two, and then this last one, we have, what is that curve? The slope is over 3 and then down 6. Over 3, down 6, that is a slope of -2, I believe. Over 1, down 2, over 1, down 2, over 1, down 2. Yeah! And let's see, I'll use this point right here. So y minus -4 is -2 x minus 2, and that would be y equals -2x plus 4 minus 4, -2x plus 0, I guess. I guess it goes through that point. It doesn't look like that in my graph, but it does. Now, if we want to find this area, we say, what's the upper function? Well, it depends, and this happens sometimes. We have this upper function from -1 to 1. So this red area is the integral from -1 to 1 of the upper function, x plus 3 minus the lower function, -2x. And let me move that over a little bit, please. No, it's not going to work. Fine. And then between 1 and 2, this green area is the integral from 1 to 2 of the upper function there is -8x plus 12 minus the lower function, which is the same, -2x dx. Now I apologize for the flaming colors. Let's tidy this up a little bit. This is the integral from -1 to 1 of x plus 2x is 3x plus 3 dx, plus the integral from 1 to 2 of -8x plus 2x is minus 6x plus 12 dx. Now, some of you may be tempted to add these two functions. You cannot add these two functions because we are talking about definite integrals with completely different limits of integration, from -1 to 1 and from 1 to 2. If this was from -1 to 1 and this was from -1 to 1, we could combine and say the 3x and the -6 was minus 3x and plus 15, but we can't. We have to do these separately. We have to call this 3x squared over 2 plus 3x from -1 to 1, and this other one is Negative 6x squared over 2 becomes negative 3x squared plus 12x from 1 to 2. And this gives us what? 3 halves plus 3 minus, squaring a negative 1 doesn't change it, 3 halves minus 3. And then over here we have negative 12 plus 24 minus negative 3 plus 12. So what happens? We have 3 halves minus 3 halves goes away, but 3 minus negative 3 is 6. Over here, that is clearly 12, and this is clearly 9. 12 minus 9 is 3. 6 plus 3 is 9. That triangle has an area of 9. There are other ways to prove that. There's this really amazing formula, if you haven't seen it before. Any triangle with sides A, B, and C, if you take the semi-perimeter, which is half of the perimeter, A plus B plus C, then the area is going to be the square root of the semi-perimeter times the semi-perimeter minus A times the semi-perimeter minus B times the semi-perimeter minus C. This is called Heron's formula. I wonder if you could prove it with calculus. I don't think you could. Maybe. Oof. Anyway, so you could conceivably use the distance formula, find the distance, the lengths of these three sides, and then plug it into that. But this is another illustration of using the area between curves by integrating the top function minus the bottom function.